Okay. So we are still at Dijkstra, and if you remember from last time, we tried to finish the proof, we could not go through, so we are going to give it another shot today. How many here remember how Dijkstra works? Okay, very nice. Okay, so let me remind you exactly what's happening. There are two almost equivalent ways of looking at exactly what's happening. So the one is with the graph itself. You're given a source node, and this view of things is that there is a particular boundary that keeps increasing slowly. Okay? And as you pick out nodes from this side, you essentially push the boundary outwards. And at every point in time, you're going to essentially get one extra node from the outside, and it just picks that up, and so on and so forth. So there is a growing tree. This is not the minimum spanning tree. This is the shortest path tree. And as you are moving outwards, repeatedly nodes come in from the outside, and you increase the boundary, and then you do a particular kind of check. So what is that kind of check? So this side, which is unknown, is essentially sitting as a priority queue. So that's on this side. And this particular side essentially is something called S, which is essentially a bag. Okay, so things are leaving here and getting in there. And how do things leave here? Well, at every point in time, you choose the one with the minimum D. So these are the D values all over the place. You choose the one with the minimum D that turns out to be this, maybe, example. So you were here, this is the one with the minimum D. You're going to bring that in, and then it has a bunch of edges going outwards. You simply go and relax each edge. Okay, and by relaxation, we simply mean you look at this D value, you compare it with the D value here, plus the weight on this edge. Okay. Previously, in the case of prim, you were just looking at some other notion of a D value, which was just being compared with the D value here, but not added to that. So essentially what was happening was that it was essentially jumping in. Sorry, you were just using this edge to see exactly how far you are. But in this particular case, the D value here is supposedly your shortest path distance from the source node. And so when you compare this D value plus this weight, and if it turns out to be smaller than the D value already sitting here, it essentially means that you have managed to decrease a bit your view of the shortest path. So you do that set of relaxes, and that is essentially going to cause a bunch of these guys to move up until you have, once again, somebody with the smallest D value in the next cycle. You pop that, that probably is sitting someplace here, you bring that in, and again you relax. Okay? Any questions about this? Okay, so this essentially tells you that every edge is getting relaxed exactly one time, because you relax an edge only when you arrive at a node who is on the back side of that edge, and that is when you relax that particular edge. And so complexity wise, every edge is relaxed once, and there are at most V of these that are going to get deleted from your priority queue. Okay? So each of this is log V, so it's V plus E log V, E log V. The point is, of course, we have an algorithm here. We have to make sure that it works right. Okay, so in order to be able to prove that it works right, we essentially went about a manner of doing it that was very much like when we did it with the breadth first search. So the first thing we did was to say that the D values, which are all infinite, and a particular node, which is the source node, which has a D value of 0, that once you go through the entire process, and assuming that these are the shortest path distances, so that is the distance of the node V from the source node, that when you go about relaxing these nodes, they will essentially come down but not fall below the shortest path distance. Okay, this is exactly like we did things with breadth first search. And the proof for this was quite simple. So, what we said is that here is a source node, and assume that this is the shortest path to V. If this is the shortest path to V, this is also the shortest path to U. Okay. So, now we can clearly see the following. If we know that the d of U is greater than equal to the delta of SU, then when we relax this H, the d of V is going to become the d of U plus this weight. Right. So, d of V becomes d of U plus the weight. Now, very clearly, the shortest path to V is either this or some other shortest path, say, which has even less weight. That essentially means that the shortest path distance from S to V is actually less than equal to okay, and this clearly tells you that. So, then what is happening? D of U is greater than equal to delta SU. So, if I plug delta SU, if I plug this in, you are going to get a d of V which is greater than equal to this, which of course is going to be greater than equal to the delta of SU. So, all we have shown is that the d values do drop, but they do not drop below the delta values. This is exactly like we did when we did it with breadth first search. Okay. So, if you remember from breadth first search, the second piece of the proof essentially was that, well, assume that you are not going to get the shortest path distances. Then we need to be able to pick a particular node where we know that it is not going to hit the shortest path distance, and we picked it up in a very peculiar way. In this case, we will do it in fact very similarly, but because the algorithm works slightly differently from breadth first search, it will be much easy to conceive of what is really happening. So, what I am going to show you is the following. Okay, this very basic fact that at the start of every cycle, all the nodes that are already in here are going to have their shortest path distances. Question is, why does this prove that Dijkstra is correct? Very clearly, at every start of every cycle, one node gets in. Right. So, if one node gets in at every cycle, by the time the cycle is done, which is essentially V times, it just goes through the whole thing V times, I will have then shown that everybody sitting in S have their shortest path cycles. So, I am setting it up in an inductive manner where my index is going to be the cycle itself. Is that making sense? So, I have a cycle every time a node comes in, and I am going to show you that at any point in the cycle, the set of nodes which are in this bag, which is not sitting in the queue anymore, they all have their shortest path distances. Okay. And we do this by induction. So, essentially what I am going to do is I will show you that in the base case it is true, and then if I prove this particular inductive case, then I know that all through the process this is going to contain shortest path distances, and therefore, when the process ends, all of us will have, or all the nodes will have their shortest path distance. Okay, so, base case. if you look at your algorithm, you will find that the base case is one where S is empty. Right? You would have assumed that you start with the source node in S and do stuff, but the way we set the whole thing up, we had all the nodes sitting in Q. We had S with a value of 0, and that's how we started the base case. This was an empty set. Okay? So, in this particular case, if you look at the algorithm from that point of view, base case is trivially true. Okay, so S is empty. Of course, there are no nodes in there, so there is nothing to check. All we now need to do is to prove the inductive case. Okay, so here is the inductive case. Just like in breadth first search, what we are going to do is we are going to prove the inductive case by contradiction. So, we are going to say, well, if what the claim is of the statement is not true, then it must have happened at some point, maybe several times. But what I am going to do is I am going to look at the first time this happens. So, there is a first time that a node got plugged out of Q thrown into S, and that is the first time that I found out that the d value of that is not its delta value. Am I making sense? Okay. Tell me if you are not following, because the argument is not particularly difficult. It is essentially induction. You look for an index, we found an index, and now because there is a possibility that this might break down several times, we are going to look for a unique one so that we can prove it using that. Same case as in breadth first search, we were looking for a unique node for which something bad happened. Likewise, here we are saying, let us assume that there is a first time that something bad happens. So, I am going to say okay, the first time, here is a node that has just gotten into S, here is my bag S, and U is that node. And I am finding out that the d value is not the same as the delta value. Okay? Okay, now, what can we say if the d value is not the delta value, given that we have proved something before? Can the d value be less than the delta value? It cannot. So, we now know, because of the previous theorem we showed, that the d value is actually strictly greater than the delta value. That is what we just realized. So, u came in, and suddenly we are finding out that the delta value of u is actually strictly less than the d value that is sitting with it, and so things have broken down. Okay, so, now let us look at the following scenario just before u is brought in. This is just before you got pulled in. What can we say about the d values of everybody just before you got pulled in? Of all the people out there, each with d values, what can we say about the d value of u, assuming that d just got into S? There are d values of people out there sitting in the priority queue, or thought differently, in the rest of the graph, and this graph is just increasing. And now I am saying I am going to bring u in. What can I say about the d value of u as compared to the d values of the other people outside? It is the smallest, right? According to our algorithm, you bring in the smallest guy. Okay. So, that much we know. Now, look at the following. So, here is the state of the graph just before u is getting pulled in. Okay. So, here is your source node. Assume that this is the capital S. These are the nodes that are already in there, and U will just get pulled in now. Okay. Let us say that U is sitting out here. Very clearly, U has to be sitting outside to get pulled in at this step. Agreed? Okay. So, now I am going to look at the shortest path from S to U. I am looking at the path itself. Now, very clearly this path, we have no clue how it looks like, but we know the following. It starts at S and maybe does that. Okay, I do not care. It starts at S, I know, and at some point it has to leave the boundary. Now, it can immediately go to U, meaning that it can start from there, come out and directly go to U, or maybe it just goes in and out and in and out, but I am guaranteed that at some point it leaves for the first time. Any questions? Are you following? How many here are not following? How many here are following? Okay, good. Yes. It turns out it is not. But I cannot start proving that piece because it is not necessary for me to prove that. All I need to assume is that if you have the shortest path from S to U, then that path will have left the capital S at some point for the first time. Beyond that, it might directly go to U, maybe come back and go through U. It is not relevant to the proof. That is what I am basically saying. So, we do not need to care. So, I am drawing you the general case. If I were to say directly goes to U, what if somebody raised his hand? What? That is not possible. Maybe it goes back and forth and my proof breaks down. So, I am basically saying here is the general case. Okay? Now, look at the following. So, when it is leaving S and going to U, this particular path, mind you, this is the shortest path to U. If it is the shortest path to U, is it the shortest path to every node in this path? Yes, right? If it is the shortest path to U, then if I give you any node in this path, this is the shortest path, because if it were not, you could have taken the shortest path to that and then gone to U, and that would be even shorter. So, we know that it is also the shortest path to all of these nodes here. Now, I am going to look at this particular edge. I am going to call that X and that Y. Okay. So, I am looking at the first, I am looking at the paths and at the point where it is jumping across the boundary, and I am looking at X on this side and Y on the outside. Very clearly, it is possible that Y is itself U. If it were so, Y could have been U or somebody else. Once again, I do not care, but I know that X is inside. What does it mean for X to be inside? X was taken out of your priority queue some point previously, right? If X is already inside, it means that at some previous step, X did get in. By assumption, X has a D value of what? Delta S X. And this is the case simply because we are saying U is the first time that something went wrong. So, we know that the D value of X is that when X got pulled in, it relaxed all its edges. Agreed? Remember, the algorithm essentially works by saying throw somebody out of your queue, relax those edges. So, when X got pulled in, that was a point in time when it did have its correct value, because if it did not, then U would not be the first time something went wrong. So, when X got pulled in, it did have its correct value and it relaxed this particular edge. That is how the algorithm works. If somebody gets pulled in, all its edges are relaxed. I'm just looking at this particular edge, and I know that at that point in past, that edge got pulled in. Sorry, relaxed. Are you with me? Okay. So now, if you remember from last time, I had shown you the following statement, that if this is the shortest path, in this case to y, and at some point in the past, the d value here, where the delta value, when this gets relaxed, it gets the correct answer. It gets you the delta value of y. This is very obvious here too. So when this got relaxed, knowing very well that this is the shortest path to y, the d value here was the delta value just before it got relaxed, and when this got relaxed, what value did y get? The d value of y at that point in the past. The delta value of y. Agreed? So that point in past, the d value of y became the delta value of y. Are you clear so far? Okay. So now what are we saying? The d value of y is the delta value of y. By the nature of this path, what can I say about the delta value of u and the delta value of y? Mind you, all these are positive weights, and the way I have drawn it is that this is the first time it leaves, u is someplace there, so u could be here, 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 we do not care. But u is farther down the shortest path. If u is farther down the shortest path, its delta value is actually larger than the delta value of y. Right? So, we know that the delta value of SU is greater than the delta value of S1. I say greater than equal to simply because u could be y itself. Do you see a contradiction now? What is the contradiction? Yes. We started by assuming that u will have a d value which is the smallest of all, because at that step it will get pulled in. And I am just showing you another node called y, whose d value has just been shown to be less than or equal to the d value of u. So, it is not possible then that u gets pulled in, instead you would have pulled y in. And that therefore produces a contradiction for us, which essentially means that this is not possible, which means that at the start of every cycle you are going to have the the delta values of the elements in S be their correct values, which is the d values. The d values be the delta values. So, by the time you are done with Dijkstra, all the nodes will have their delta values, and so the theorem is correct. Okay? What Dijkstra shows you is that all you need to do is be extremely smart about who you are going to relax. If you just look at it from above and not see who is getting popped and thrown into S, then you will just see a bunch of relaxations happening. Okay? So, you look at the graph and Dijkstra will say, okay, relax that edge, that edge, that edge. You do not realize that they are edges coming out of a particular node. And then it will suddenly say, okay, relax these 3 edges, and then relax those edges, then relax those edges, and so on and so forth. It will do it only once. It will essentially, if you just keep your eye on a particular edge, you will see that that edge got relaxed just once. So, Dijkstra manages to relax edges in such a manner so as to just go through every edge exactly once and get you the shortest path by the end of that. Okay? The problem with Dijkstra is as soon as you have an edge which is negative weighted, this proof falls apart. Okay? Assume that everybody from here onwards were all negative edges. By negative edge, I mean an edge with a negative weight. Then I could not have claimed that the delta of u is actually strictly greater than or equal to the delta of y. You could have come here and then dropped your weights. And if that were the case, all the stuff that I did would fall apart because I was trying to sandwich the value of d of u. So, in a case where you have once again a directed graph, but there can be edges which are of negative weight, Dijkstra will not work. You need to do something else. Now, you might ask, why is it that you want a negative weighted graph? Well, it turns out, and I do not want to give you the answer, I want you to think and see, are there problems where you can essentially see that or map that to a graph theoretic problem where you are looking for shortest paths, where the weights suddenly turn out to be negative. It turns out that there are cases. Okay, so, from an algorithm's point of view, we really do not care. Well, we do, but here is just a way of solving problems. You look at a problem and say, what if an edge is negative? Now, tell me this, under what situations, assuming that you can have negative edges, what do you think is a situation where the graph will not have shortest paths? I allow you negative edges, and I am saying that under the assumption that there might be some negative edges, can you think of a situation where the graph just simply does not have shortest paths? By which I mean that if you show me a shortest path and claim that that is the shortest path, I will show you another path that is shorter. Negative cycles, right. So long as there are no negative cycles, you can still have shortest paths. Soon as you have a negative cycle, all hell breaks loose simply because you can go through that cycle one time and drop your weight, do it one more time, drop your weight, one more time, and so there is no bottom. So, here is a more general version of the shortest path problem, where you are allowed negative edges, edges with negative weights, but what you are not allowed is cycles with negative weights. And if you are going to propose an algorithm for a graph which has negative weights, you have to do two things then. When you go through your solution, you not only have to say that these are the shortest paths, but if the graph has a negative cycle, you have to stop and say at some point, I do not know when, come back and say, look, there are no shortest paths. Okay. The solution to this is something called the Bellman-Ford algorithm. So, the Bellman-Ford algorithm as compared to the Dijkstra are both single source shortest path. But this one allows negative edges and calls out negative cycles. Okay, so, it not only has negative edges, when it runs through the entire algorithm, it will come and tell you that there are no shortest paths because I have found a negative cycle. I am not going to do Bellman-Ford right now, because now that the name has come up, this is the person who did dynamic programming. So, what I am going to do is I am going to show you Bellman-Ford later, and when you look at the algorithm, you will not realize that it is a dynamic programming algorithm. I will then step back and show you that it actually is a dynamic programming algorithm. Unfortunately for you, you do not know what a dynamic programming algorithm is. So, there is no point me doing that until you know what dynamic programming is. Okay? How many here have heard about dynamic programming? How many know what it is? Very nice. Okay. Well, it turns out it's a very peculiar name because of historical reasons. Dynamic programming to you will turn out neither to be dynamic nor programming. Long back, programming meant something slightly different, not the Java programming and the C programming that you do. It was mostly related to math programming, because the people of the industrial engineering department, they were writing out these big so-called math programs to try to optimize where material has to go and where material has to leave and how much you have to load on a train and so on and so forth. They still do it, and they make a lot of money for themselves and for the train companies trying to solve for them. If you have this very large network of warehouses and trains, how is it that you are going to load things onto trains, and which trains will carry which stuff so that you get the material to the various places at the correct time? Our own industrial engineering department does that. And the way they used to at that point in time solve these problems is write something called a math program. Okay? Many of you do not know this simply because you probably have not taken machine learning, in which case if you did take machine learning you would have some sense of it. They do something called convex programming. Okay? So, the programming part comes from that kind of thing, the math program, the linear program, the convex program, and so on and so forth. That is where the programming comes. It is not the Java and C programming. The dynamic part of things you will not be able to see immediately. But if you look at dynamic programming as the way people generally pitch it, you will get the complete wrong idea. Dynamic program is essentially a very simple concept. It should not even be given a name. Okay? Dynamic program, you never say I am going to try to solve a problem using dynamic programming. What you first do is you look at a problem and say, hey, I have found a recursive solution to a problem. Dynamic programming has everything to do with you having found, first of all, a recursive solution. If you do not find a recursive solution, then you will not be applying dynamic programming to this problem. So, take dynamic programming out of your head and just first of all look at a problem and say, can I look for a recursive solution? It is when you find a recursive solution that you play a trick. And I do not want to tell you that trick. I will give you an example, and then you will slowly start realizing exactly what is happening. Okay? So, let us take the following example. So, here are the Fibonacci numbers. Okay, so, f of 0 is 1, f of 1 is 1, we can, and f of I plus 2 is f of I Okay, we know about these things. Sometimes it is 0 and a 1, sometimes it is 1 and 1 and a 1, and it does not make a difference. So, you will just have one additional number which will essentially kick up linearly as you go. It does not matter. The main thing is this is the recursive solution for f of I plus 2. So, if you want the Fibonacci someplace, you solve for the Fibonacci the previous one, solve for the previous one, add them up, produce the next number. How would you code for this, given that I have given you a recursive solution? So, I say I am writing a procedure. The reason I am showing you this is because here is a very simple example where the description or the definition of the function itself is recursive. So, we do not have to look for a recursive solution, we have a recursive solution. Okay, so, this is our recursive solution, and I am trying to write the program that you would write, the simplest program that I can write. Okay. Very obviously, if you are going to write it in a recursive manner, you take care of the base case. So, if you say if n equal to 0, return 1, right? You take care of your base case and you just write your recursive case. Any questions? My question to you now is, what is the time complexity of this? What is the time complexity of Fibonacci n, which I will call T of n, which is not the same as f of n. F of n is Fibonacci of n. T of n is the time taken to solve a problem of size n, when n is some number. How would you go about finding the time complexity? Takes you back several weeks. You were doing this a lot. And if you remember, whenever you have recursive algorithms, what do you get there? You get a recurrence relation, right? So you are going to say that T of n, if you look at this, is going to be the time taken to solve this problem plus time taken to solve that problem plus some constant maybe. Let us for the moment just forget the constant. So I know that T of n is going to be greater than or equal to this. Let us just do a very simple relation. I am just claiming that in order to solve a problem of size n, I have to solve a recursive call here, I have to solve a recursive call here. I am going to assume that addition takes no time, so that makes it equal, I am done. Does this look like something that you know? What is T of n? Can you solve T of n? You are allowed to choose any base case. Can you solve for T of n? T of n is T of n minus 1 plus T of n minus 2. What is T of n? Unfortunately for you, you are looking on that side of the board, you are not looking on this side of the board. What is T of n? Do you understand my question? I am trying to solve for this, right? I have given this in your exam and you are sitting with this question in front of you and you have to say what T of n is. Big O of something maybe, but maybe you know what T of n is. T of n is the time taken by this algorithm to solve a problem when n is a number that has been stuck in. You do not see the connection. What is f of n? I was smart enough to have written this out slightly differently. Is that true? Can I claim that that is the case? Okay, it's the same equation. And as I said, you can assume anything for your base case. I'm going to assume for f0 and f1 or t0 and t1, f0 and f1. Okay. So this algorithm that looks very small and very clean, the time taken by it to solve something of size n is the Fibonacci number itself. You clearly know that Fibonacci numbers rise exponentially fast. And so this algorithm that looks very clean, right, is not a good algorithm at all. It is going to take you exponential time to solve the Fibonacci number n. But you know that it's not a difficult problem to solve. It should not be taking you so much time. What is happening? take a few moments and look at this and tell me what is happening. Why is it taking so much time? I just showed you a high level analysis of things, and I guarantee you I did not make mistakes. I did not trick you. But the solution that we are seeing seems to be taking way too much time. What is happening? Yeah. So yeah, you can see it. What is really happening is that in order to solve Fibonacci of n, you make calls to Fibonacci of n minus 1 and n minus 2. Right? So first you make a call to Fibonacci of n minus 1, which goes back here to solve, makes a call to Fibonacci n minus 2, which goes on and on. Okay? And the whole thing is sucked up at the top for Fibonacci n minus 1, and then you go and make a call to Fibonacci of n minus 2. Not knowing that previously you had made a call to Fibonacci of n minus 2, and so you resolve this whole thing. You are solving the same subproblem over and over again. That is where all the wastage is. You just didn't see it. So if that is the case, what would be the obvious thing to do? If you know that you are solving the same problem over and over again, what would be the natural thing for you to do to speed things up? Yeah. Store it someplace. Soon as you solve a problem and it's a sub-problem, just store it. Next time around, don't go and try to solve it. Go and look and see whether you have the solution to the sub-problem. There is nothing deep about this at all. If you find out that your algorithm is stupid enough to be solving the same thing over and over again, solve it for the first time and store it. Next time around, look at it and pick it up. This is all there is to dynamic programming. All these years of waiting to know what dynamic programming is, and all it is that if you are solving a subproblem more than 2 times, just go and store it after solving it the first time. There is nothing else, except that usually if you write things in such a way where you are going to solve a subproblem and store it someplace, and the next time around you are going to go and pick it up, it probably is a better way to actually do it in such a manner that you do not have to solve it and then look for it and so on and so forth. It usually turns out that when you hit scenarios like this, if you solve the subproblems from below, instead of starting at the top and making recursive calls to subproblems, we usually find that it is better to just start from below and build the whole thing up. That way you can immediately see where the solutions of the subproblems are, and you build the solution for the slightly larger problem using the solutions to the subproblem. So usually when you see a scenario like this, you essentially take your recursive program that you have, which came because you found out that there is a way of solving it recursively, and instead of solving it from n towards n minus 1 and n minus 2 and so on and so forth, you flip the whole thing. You start solving the problem from 0, 1, 2, 3, 4 until you hit n. That then allows you to be able to put together subproblems. So what you do is you have this entire array or whatever you want it to be, so that you can store the subproblems. If the subproblems are indexed by 3 integers, then you have a queue. If the subproblem is indexed by 2 integers, you have an array. If it is indexed by 1 integer, you just have a single array, and so on and so forth. But these are the ones that are basically holding the solutions to your subproblem. And what you do is, at the next step, you are taking this n, pushing it from equal to 0 or 1 or whatever be the base case, and you push it upwards. And at each time, you take subproblems from below and plug it into the next level. At the next step, you take subproblems from there and plug it into the next level. Now, sometimes what is going to happen is that somebody here is going to get a subproblem from 2 levels below, maybe 3 levels below. Fibonacci itself does that. and you build it until you hit the top, and you spit out the answer. So, all your dynamic programming solutions that you look at will look like that. Although inside of dynamic programming, there is no necessity that you do it from the bottom to the top. Just that when you solve a problem, store it. So, in the case of Fibonacci, if I still wanted to do it in this manner, I would essentially go down to the base level, and soon as I hit an answer, I am then going to percolate the answer up completely, and that will immediately solve my problem for me. Okay. So, let me give you the other version of Fibonacci that you could write, and immediately you will see that even though it does not look like dynamic programming, it is actually dynamic programming. Okay. So, this is my other Fibonacci. Okay. So, what I am doing is essentially how you do Fibonacci. You have 0 and 1, you add them up to put it in the next place, add them up to put it in the next place, and so on and so forth until you get to n, and that is it. You spit out. That is what we are doing. We are setting two variables, 1 and 1. If you want, it can be 0 and 1 depending upon how you define Fibonacci numbers, and then you simply have a loop that essentially adds these two numbers and then pushes the answers back. Okay. So, I want to reuse these two. So, temp 0 becomes temp 1, and temp 1 just gets the value of answer, and next time around you are going to get a new answer until you hit n, and that is it, you spit out answer. This does not clearly look like dynamic programming to you, but this is dynamic programming. Dynamic programming is in your head. When you take a problem and solve it a particular way, you write it in that particular manner, and what you end up seeing is something called dynamic programming. So, here is my dynamic programming solution to solving Fibonacci numbers. Okay. Let us stop here. When I come back, I will take this concept and show you that it does apply to single source shortest path, but that is next time.